So now we're going to consider a new use for our interpolants. So as usual, the setup's going to be that we have interpolation nodes numbered 0 through n. But now we're going to restrict them to a special case where the distance between any pair of nodes is constant. So this will be equally spaced, which another way of writing it is that t sub I is some left endpoint a plus I times h. I running from 0 up to n, and that means that h has to equal the right endpoint minus the left endpoint over n. So the first node is A, the last node we'll call B. Okay, and we're going to have data, y sub I, which now is the value of some function at ti. And so now the question we're going to ask is, how can we find f prime at ti? Well, just given data, we can't do it exactly. If you think about it, f prime is defined as the limit, right, of a difference as h goes to 0, and we don't have values of the function for all those different values of h. So we can't do a limit, but we can approximate it. So we're going to call z sub I an approximation to f of t sub I. And that we can find. And one way of doing this is to take the data, right, turn that into an interpolant, and then differentiate the interpolant, which is another function, and then you evaluate that derivative wherever you wanted it. So that's the framework that we're going to use. So the first step is you choose some subset of nodes near the one that you're interested in. Right, so we might say choose the neighbor to the left as well as ti, or of course you might say choose ti and its neighbor to the right, if it has one, right? So I couldn't do this one if I is equal to n, because then I'd have to access a node that doesn't exist. All right, and what we'll do is we'll represent these symbolically. So I'll draw in symbols at each of these nodes. All right. And the key or the legend to these symbols is that, I either have a circle or a square, meaning a value of f prime or a value of f, and it's either empty or it's filled, right? Which means the value is unknown to be found, or it's known, so it's used to find the others. Okay, so these are called stencils. So this stencil tells you, right, to find the derivative at one point, you use that point and the point to its left, and so on. Okay, so our first example of this will be, actually I'm going to use the one on the right here. So take this case. All right, so I have to find a polynomial that interpolates from ti to ti plus 1. So p of x is the linear function between those two. So I'll take x minus ti times the slope, which is going to be yi plus 1 minus yi over ti plus 1 minus ti. Okay, so we can plug in what's known in that ratio. This is just f of ti plus 1. This is f of ti, and the denominator is just h. Okay, now I differentiate. It's a linear function, so I just get the slope. All right, and the derivative is actually a constant, so that means that p prime of ti is just that constant. Okay. So this leads to what we call a finite difference formula. All right, so f prime at t sub I is approximately f at ti plus h. Okay, so it's traditional to write everything in terms of that one point, ti, over h. All right, and then we can make the observation that this formula actually exists independently of all those nodes, right? I'm only referring to the point ti, so ti could be anything. It could just be x. So usually you'll see these written more like f prime of x is approximated by f of x plus h minus f of x over h. And when you write it that way, you realize, oh yeah, that's just how we started out defining the derivative, right? The slope of the secant line. In particular, this is called a forward difference, because to find the derivative at x, you look forward, you look to your right. If we go back to our stencil, we can fill in a little bit more information. Okay, so what this says is the weight, sorry, I'm getting ahead of myself. You take 1 over h times the value forward minus 1 over h times the value backward. Now it turns out that h in the denominator is always there, so we don't normally write it. And these constants down here are called the weights of the formula. They tell you how much weight each of the nodes that you're using has in the result. All right. So how do we assess the accuracy of this process? There are a couple different ways of coming at it, but the easiest is Taylor series. So we note by writing f of x plus h around the value h equals 0. Should put the h first, plus 1/2 h squared f double prime of x plus dot dot dot. Okay, if we subtract f of x, right, then that term's gone. We divide by h, we get f prime of x. So if we rearrange this slightly and put the f prime by itself, right, then we get f of x plus h, that series, minus the f of x divided by h. And then what's left, well, the first term is plus 1/2 h f double prime of x. And then the next term, here it would have been 1/6 h cubed, but I divided by h, so it'll be h squared times a constant, and I'm just going to call that O of h squared, right? So that's our big O notation that tells us the rate at which that term goes to 0 as h goes to 0. So this is a good formula as h goes to 0, right? The error, and ignoring this term relative to the first one here, this is sort of the first error term. So the h to the first power, means first order accurate. That's an error proportional to h to the first power. And then this 1/2 here could be called the error constant. The error constant is much less important than the order of accuracy. All right, so second case to look at is this one, okay, which is a backward difference. So the derivation of the formula goes much the same way. The result also looks similar. The weights are -1 and 1, which tells you, or should tell you, exactly how to write down the formula. So the circle tells us that f prime of x, that's the location of the circle, is 1 times f of x minus 1 times f of the node to the left. Right, which is just an alternate way of computing or estimating the derivative. And doing the Taylor series around h equals 0. Right, so this term has some, every other term is negative now. The squared terms are positive. So again, the f of x's cancel out. The first term is f prime of x. The next term is, well, let me write it out. That'll help. All right, so that's equal to sorry, this is not f prime of x. This is the finite difference, right? So it's just equal to the line above it. And then this is minus 1/2 h f double prime of x, and then the next term is higher. So again, this is first order accurate. All right, so you can just repeat this process for whatever nodes you select. I'll show one more because it's really, really important in practice. And that's a case where we use some symmetry, and you include both the point to the right and the point to the left. So this would be called a centered difference. All right, and in this case, the weights are -1/2, 0, and 1/2. Okay, so 0 weight means that that value doesn't even appear in the result. So the formula is going to be, normally it's written with the 2 in the denominator, so it's it's 1/2 times, and we usually start at the rightmost node and work back, f of x plus h plus 0 times that one, minus 1/2 times the other one, so minus f of x minus h, and then that factor of 2 appears in the denominator along with the h that's always there in the denominator. And if you do the Taylor series analysis, you'll find that the error is h squared over 6 plus f double prime of x. And the h cubed term cancels out, so in fact the next one is h to the 4th. And so now we see, because of the h squared, this is second order accurate, which is actually a lot better than first order. Right? If I take h in half, then first order only gives me a reduction in error of 1/2. This gives me a reduction in the error of 1/4. Okay, the square. So that's nice. Okay, so one last thing to tackle with these. let's go back to our vector of data. And we want to find a way to map that to the vector of approximate derivative values. Okay, so the analog, this is discrete. The analog in the continuous case is that you're mapping a function to its derivative. Right? And we can write that f prime of x is d by dx of f. Now, one way of interpreting this equation is that the derivative is what we call an operator, which is a function on functions. It's a way of mapping one function to another function. But what's important to us is that it's a linear operator, right? Derivative of a sum is the sum of the derivatives. The derivative of a times f is a times the derivative of f, if a is scalar, a constant, sorry. So that means that hopefully our discrete case is also a linear operator. And a linear operator is always a matrix, and I've already messed it up by writing these backwards. So z is dx times y. And this dx is called a differentiation matrix. Okay. So where do we get the differentiation matrix? We do it by filling in formulas, right? So we'd probably like to use that second order formula where possible. So we might say zi is defined by yi plus 1 minus yi minus 1 over 2h. That would be centered. But I can't use that when I is equal to 0 or I is equal to n. I'd be accessing a value that doesn't exist. And so I'm forced to use something which is either forward or backward, what we would call one-sided at the boundaries. So I'll just make the best that I can out of it. All right, so let's write this out with some care. All right, so I'm going to take, there's a 1 over h in everything. I'm going to take that out in front. So I'll have a matrix of constants. And that multiplies the data. Okay, so if we look at the row z1, that's y2 minus y0 over 2h. All right, so a half times yi plus 1. In this case, that's y2, right? y2 is in the third column. Plus 0 times y1 plus minus a half times y0. And everything else in that row is 0, right? So this is the inner product of this row and that column gives you this formula with I equals 1. All right? Now let's skip down to zn minus 1. This is 1 half yn, which is at the last column, plus 0 times yn minus 1 minus a half times yn minus 2, which is just to the left. So you see how we're just filling in the weights, right? That's what's so convenient about writing them that way. Now, for y0, we'll use a forward difference. So that's 1 times y1 minus 1 times y0. And at the right end, I'll use a backward difference, which is 1 times yn minus 1 times yn minus 1. So this is one possible definition for dx. But there are many, many ones that we could choose from. Now, it might seem like a bad idea that first and last rows are first order accurate, the others are second. You can fix that. Turns out you don't always need to in context, but that's a detail we don't have to get into. The important thing is to be able to use finite differences to write down a differentiation matrix.